So I'm going to start this talk with acknowledgments, just in case we run long and I don't have a chance to get to them. So these are the people that were really crucially involved in the work that I'm going to show today. Yuancheng Liang, who's here, really worked with me side by side from the very beginning of this project, and I can honestly say this research program probably wouldn't exist without him. And Asya Zebud, who's at Princeton now, she led and recently published the second study that I'll talk today about communication. And Chris Honey, Esther Young, Uri Hassan, and Ken Norman all contributed really essential conceptual and material pieces of the work that you'll see today. Okay, so I'm going to talk today about patterns of brain activity that are shared across people. But let's start with something a little more familiar. So I want to first talk about patterns of brain activity that are common between encoding and retrieval. And this is often referred to as neural reinstatement, the idea being that reactivated patterns in the brain reflect some kind of memory retrieval. So when you remember a prior experience, you're to some extent mentally reliving and neurally re-experiencing that event. So the study I'll talk about is a memory experiment in which we really emphasize naturalistic perception and behavior by using movie viewing for the perception and spoken recall for the memory. And I'll first talk about reinstatement effects in that paradigm, and then we'll extend that to talk about cross-subject similarity in brain patterns. I'll talk about transformation of neural patterns between perception and recall, and then tell you about a study where we trace neural signatures between brains during communication. Okay. So here's the paradigm. I'm going to give you a sample of what people experienced in the scanner. We're watching a lot of movies today. It's a short clip. So they watched 50 minutes of Sherlock. It's the first episode of Sherlock. And this clip is from somewhere in the middle of that.
What about these suicides then, Sherlock? Thought that'd be right up your street. 3 exactly the same.
4. There's been a 4th. There's something different this time.
A 4th?
Where?
Okay. After people watch the movie, then they stay in the scanner and they're asked to verbally describe everything that they can remember from the movie from start to finish. And they're really not given much more instruction than that. They just go. There's no cueing during this memory. They start at the beginning and they try to retell the entire story. So I'm going to play a clip of one person doing the recall for the scene that you just watched. And since the movie is 50 minutes long and that clip was from the middle, by the time they get to this point in their recall, it's at least half an hour later, probably. All right?
So they have this exchange where Miss Hudson comes in, asks if everything looks okay, and she picks up the newspaper and she's asking Sherlock about the murders that have happened. Sherlock briefly looks outside and he sees that there are cop cars, and he says that there's been a 4th murder. And something must have been different, so that's why they're there. And just moments later, the chief walks in.
So you can hear how good that is. People are really, really good at this task. And that actually surprised us at the very beginning, too. We didn't think that we were going to be getting 30 or 40 minutes of recall from people for a 50-minute movie. But people's memory is very detailed for this kind of material. And they're able to kind of complete the story without any prompting, I think, because you naturally cue yourself. So you remember one scene, it logically leads to the next one, and they just go and go. The only constraint that we put on them was that they should try to talk for at least 10 minutes, which people initially think is going to be challenging, but then it turns out to not be at all. It's very natural behavior. Okay, so to deal with this data, first we take the movie and we segment it into scenes. So these are director's cuts. They're very obvious boundaries in the movie. We have 50 of these scenes. and then we label each scene and go to the recording of each person's description and try to find those same scene boundaries in the audio. So not everybody remembers every single one of the 50 scenes, but we get about 30 scenes on average. So now you have timestamps that relate the recall to the movie. And this is a diagram of one person's behavior during this task. So you can see time during the movie on the y-axis, 0 at the top, and then time during recall is on the x-axis. So each one of these rectangles is a scene in the movie, and it just shows you the progression of their recall. If you have rectangles that are off of the diagonal, that means that they were recalled out of order. And this is pretty typical of what you see, a fairly complete recall where this person is hitting most of the scenes, and it's actually mostly in order as well. And maybe the most surprising thing is that it's pretty straight, this diagonal line. So that means that whatever compression rate is happening as people start to describe the movie, it's relatively constant as they go on. So he takes about half as long to describe each scene as he did to watch it. This is all of the subjects. So you have 17 subjects. The diagram's a little different, so each line segment corresponds to a diagonal of one of these rectangles. But you can see the spread here, people taking anywhere from 10 minutes to 45 minutes to describe this 15-minute movie. All right, so now that we have the data, we can look for reinstatement in the brain. And where should we expect to find it? Well, the brain is hierarchically organized, as Chris talked about yesterday. So information from the senses arrives first at low-level sensory areas in red here, and then passed up to higher areas of the brain, becoming more aggregated and abstract as you go up. So during the movie, you're receiving this continuous auditory and visual input. So you might expect to see a reinstatement during recall in these low-level sensory areas that process auditory and visual information. But the movie is also driving a lot of other regions in the brain and in this hierarchy. So you also have high-level regions driven by the movie that process things like meaning and emotion and features of the stimulus that are abstracted away from the specific sensory details. And if you look at these high-level regions, they overlap very well with a well-studied network, the default mode network. And this network is implicated in a huge variety of different cognitive states, but just a few. So it's active during autobiographical memory and recollection, and it's thought to integrate information over long timescales, also like Chris talked about yesterday. And probably the most relevant for this talk is the idea that activity in this network reflects situation level information. So kind of the schematic description of what's going on in an event, like the locations, the characters, the contingencies and actions that make up this current episode. So to the extent that you think that kind of description information is shared between the movie viewing and the recollection of that scene, you should expect to see reinstated activity in this network. Okay, the analysis goes like this. So you take any region of the brain that you like, and you get the movie data from that region and the recall data from that region for the same scene, right? So like scene 1 of the movie and then the description of that scene. And then we're just going to average over time, throwing away all of that temporal information for the scene, to get a vector of voxels for each movie scene and for each recall scene. Sorry, those got turned sideways, those vectors. And just calculate the correlation between them. So you're looking for a measure of similarity between the pattern of activity during a movie scene and its corresponding recall scene. And you can do that for every scene in the movie that the subject recalled. And your statistical analysis will look at the matches versus the non-matching scenes. So you can also do correlations between all of the non-matching scenes, right? And we'll do it in a searchlight across the entire brain to recover a map of all of the regions where you actually had a match between the patterns of brain activity at movie and recall for that specific scene. And what you see here is basically the default network in some high-level visual areas. So you have posterior medial cortex is probably one of our strongest reactivated areas. medial prefrontal cortex, parahippocampal cortex, angular gyrus. And just to show you how strong this is, so for each of our 17 subjects, you can see the non-matching scenes, or the null distribution, are those black squares centered around 0, and then every single one of the subjects in posterior medial cortex, you'll see this positive reinstatement effect. And remember, this has to be scene specific. So we're talking about like a fingerprint of activity for each scene that is unique to that scene. All right, so summarize this section. During free spoken recall of a prior experience, in this case, a movie, we saw neural patterns that were activated scene by scene, and that was observed throughout the default mode network, but not in the lower level sensory areas, even though those areas are driven during the movie. Okay. So this analysis up to now is all performed within brain, which is how multivoxel analysis is typically performed. But we're going to next look at the extent to which these patterns are shared across people during each stage of the task. And this is just using anatomical alignment, no hyperalignment. Is that what your question was going to be? Oh.
So when you showed the plots of people like calling scene by scene, right, there were a few situations where people would call scenes out of time. So did that affect the classification at all? Like if there were, like...
Each scene is treated independently, so there's no order information remaining once you do this analysis. Yeah. I will say about those scenes that are recalled out of order, usually, almost always, it's not the case that a person thinks that scene actually occurred at that point in the timeline. They forget to mention something, and then they'll jump back and talk about it later. Okay, so not using hyperalignment, using only anatomical alignment, we're going to look at the quality of shared patterns between people. And so what can we learn by doing this kind of analysis? Well, in the study of sensory systems, it's well known that there are topographic maps across the cortex. So these are areas where you have functionally organized responses that map onto regions of visual space or onto auditory frequencies or somatosensory information. And these maps are fairly well preserved across people. So I'm showing here a probabilistic atlas of visual areas, and this is made by anatomically aligning brains together. And based just on this kind of alignment, you can get a pretty good correspondence. You know, it's spatially coarse correspondence, but it's a correspondence across different people of where these maps fall. So this kind of mapping is done using simple stimuli like these flickering checkerboard wedges and rings that contract and expand. So for example, if the ring expands, it might move gradually across. The activity will move gradually across the surface of this map. But what about our high-level regions that we saw in our reinstatement analysis? You know, they do not respond to flickering checkerboards in this way, and there are no sensory maps up there. So what I want to show you is that using this complex natural stimulus, you can reveal that there is spatial organization up in those areas, even though you don't have these same kinds of sensory maps. So we're going to do the same kind of analysis, but now using only the movie data. So for each person, you again have an average pattern of voxels for an individual scene, and now you're doing the correlation to another person viewing that same scene. And do that for all 50 scenes in the movie, and again, your statistical thresholds involve building a null distribution from non-matching scene correlations. And now, when you look at this map, you see matches across people, not only in those high-level default network areas, but also in the low-level sensor areas that we're missing in the reinstatement map. So everybody's getting the same audiovisual stimulus, and their brain is being driven both temporally and spatially in a similar way across people. There. And I can show you the individual subject results again. So these matches are higher than what we saw in the encoding versus recall correlations. Again, when everybody is getting the same stimulus, you're getting a pretty good correspondence between subjects. All right. I can also pose this as a classification problem, right? So what you can do is say, here we've split the data into 2 independent groups, so you have 8 and 9, and average that down into 1 average brain for each group, and then ask for each scene, can I locate that scene in the other group? So 1 out of 50 is scene 1 going to have the highest correlation with scene 1 of the other group, and if it does, then it's a hit. And the green dots here are showing you different splits of the subjects into 2 groups. So, with the chance level of 1 over 50, you can do this classification at about 35%, which is very good. And you can also look at the classification rank for individual scenes just to make sure that it's not like a couple of scenes that are driving this. And you see pretty good selectivity across the board for these scenes. Now, when you anatomically align subjects to each other, you're necessarily throwing away fine scale spatial information. Nobody is saying that there's that kind of alignment going on here. And I just want to show you what the kind of topography looks like for this data. So this is raw data as Z-scored. It's not a correlation map. And you'll just see for each one of these brains is the average of half of the group. So I'll show you what this slice of the brain looks like for each scene in the movie. And what you're looking at is the correspondence between the 2 maps, because they're independent subjects watching the same movie. To the extent that you see similarity, you have signal that's driven by the movie, not idiosyncratic signal, one scene at a time. And I think it can start to give you a sense for what is shared across people. There's definitely some variation across the scenes, but there's, I think, visible similarity between the 2 groups. And it's kind of, there's a lot of gradients and it's pretty spatially coarse. This display kind of makes it look coarser than it really is because it has to be Z-scored across the entire slice. But you can also look at one little region and see that there's a little bit of detail inside posterior medial cortex that's nonetheless shared between the groups. So this is the kind of signal we're dealing with. And just for fun, it's also good to see what it looks like at the highest temporal resolution available in the fMRI data. So there's a lot of bubbling activity in here, and the analyses that I've showed you, or will show you today, all involve kind of averaging across a lot of this time, but it's going to be important to recover this information because you can see that it does correspond between people. Okay. So you saw that during this shared movie viewing, shared experience, spatially coarse patterns were very similar across subjects, and that was observed throughout low-level sensory areas as well as the higher-level areas in the default network that we saw during reinstatement. And everybody was seeing the same movie, and so I think it makes good sense that you're going to see similar signal and activity across different subjects. And our next question is going to be considerably more challenging. So we're going to look at patterns of activity across people during a collection. So the reason this is challenging is that during recall there's no stimulus at all, and the only thing that people have in common with each other is that they're remembering the same thing, right? So they're describing some scene in the movie, saying whatever they want, remembering whatever they happen to remember from it. Everybody describes the movie in their own words, and the amount of time that they spend talking about that scene could vary quite a lot, and the details that they recall actually differ a lot too. So just as an example, there's the very first scene in the movie where you meet Sherlock is kind of a weird scene. He's in the morgue and he has a riding crop and he's whipping a corpse. You don't know why. And there's this dramatic music playing. And then also in that scene, there's a new character, which is like a lab assistant, and she definitely is interested in Sherlock and is trying to flirt with him, and he kind of isn't getting it. Okay, so this is one person's description. He brings them to a morgue, and Sherlock Holmes whips a dead body. I don't really know why. I guess he's wondering about the bruising pattern, which is what's happening. So that's a very short description of this 54-second scene. Another person says pretty much the same thing, but does remember that there's this lab tech there. He's talking to a lab technician who has a crush on him, and he doesn't pick up on her cues. And then this person, I won't make you read all of it, but this person actually has a different interpretation of what's going on, because he says she's clearly trying to ask him out and he hardcore rejects her. And then she asks if he wants to get some coffee later, and he's like, yeah, black one sugar, which is a sarcastic response. So these people had different memories, or at least different descriptions of what happened during that scene. But at the same time, there's some commonalities between what they said. So everybody pointed out where that action took place. Everybody has Sherlock Holmes in the scene. Everybody remembers what he was doing and why he was doing it. And at least 2 people mentioned this other character. All right, so we're going to try to take advantage of these commonalities in people's memories and look for neural signatures that are also similar between people in a scene selective way. And again, the analysis is just to take each scene, this time from the recall data of each person, and then average it down into one pattern for the scene and compare it to the scenes to the data of other people recalling the same scene, and compare it to the non-matching correlations. So this map shows you where in the brain there are similar patterns across people during this recollection, during this shared memory. And again, we have default network areas and a little bit of high-level visual areas. And the strength of this correlation is pretty comparable to the movie versus recall similarity, actually. And I'll also mention that movie versus recall similarity is quite similar whether you do it within or across subjects. I'll show you the classification version of this. Your chance level isn't 1 out of 50 anymore. It's more like 1 out of 45, because it requires at least one person in each group to have recalled the scene. But classification accuracy is still around 18%. And I'll show you, just to compare with the movie. The movie stimulus definitely aligns people better, but there's definitely some shared information here that's being revealed that allows you to classify across subjects which scene you're looking at. Okay. So when different subjects verbally describe the same movie scene, you see these similar scene-specific neural activity patterns across brains. And that was observed throughout the default mode network, but not in low-level sensory areas. Okay, so let's go back to the design again. You have people watching the movie, and you have them performing this memory task, and you look at, you can find these reactivated patterns as they're doing the task. But it's not a perfect match, right? This reinstated activity is an imperfect representation of the original scene. And you can definitely believe that people's memory is not a perfect recreation of the original experience. And one possibility is just that there's forgetting. And another is that there's some useful way that patterns are transformed, or memories are transformed between your perception and your recall. Because a memory system that records your experience perfectly wouldn't really be that great. Right? So memories can benefit by being transformed. They can be compressed, they can be informed or changed by your existing knowledge, and they can be generalized to other situations. And those are all kind of useful ways that your memory could change from the original experience. So for example, if you go on vacation and take 1,000 pictures, when you get back, maybe people don't want to see all 1,000 pictures of your vacation. It would be more useful for them if you could summarize that a little bit and say, oh, these are like the kind of general cultural motifs that I observed and the natural phenomena that I saw in the food that I ate. So there's definitely a usefulness to certain kinds of transformations. So we're going to look for exactly this in the brain. We're going to ask, how do neural signatures change between perception and recall? And there are kind of 2 scenarios that I'll propose here. One is that they change in a unique way for each person. So this can be like basically a lossy version of the original, noise added for each person, or their own kind of special way of remembering that just isn't the same as anybody else, right? So you have a unique change for each person between perception and recall. But another way it could happen is that you have a systematic change across people. So everybody's memory does change from the original, but in a way that is common. So in order to look for this, we can take our movie viewing data and each person's recall, and I'm going to try to walk through this in a way that makes sense. So the idea here is that if everybody's neural signatures are changing in an idiosyncratic way, then recall similarity has to be lower than movie recall similarity. So in this diagram, if you start with two brains and they have the same movie pattern at the beginning, and then you add this uncorrelated information, you're going to see that the similarity between their two recall patterns has to be lower than the similarity of movie to recall. And on the other hand, if you're adding correlated or similar change for each person, then it becomes possible for those recall patterns to be more similar to each other than they are to the movie pattern. So it's not necessary that it's higher, but it becomes possible. So what we looked for is regions of the brain where recall similarity was higher than movie recall similarity. And we found that in these regions, you have a little bit of high-level default regions and some high-level visual areas. It's not as much of a match for default network regions as I expected, actually. So I think this map is interesting and requires a lot of follow-up. One thing that you want to know is whether the transformation was actually useful in some way. And we do have one data point that speaks to that. So if you go to posterior medial cortex and you ask, how much did the patterns change for each scene? These data points are the 50 scenes. You can find that the more that the pattern changed between the movie and the recall, the more likely it was to be remembered. So the greater the number of people that remember that scene. And the kind of speculative explanation for this is that some scenes are more canonical than others, or tropey. You could say that they have a strong schema in the collective. And imagine that there's like a car chase scene. Even if you don't remember that scene very well, you might be able to fill in some of the details based on what you know about car chase scenes. And scenes that have this kind of stronger schematic content might actually be better remembered. So that's also work that needs to be followed up. Okay. So the next thing we did is we extended this paradigm. You have your movie viewers and your speakers. And what we did is we recorded one of the speakers. We took their audio and played it to a new group of people. So you have people who have never seen the Sherlock movie before, now listening to a roughly 20-minute audio description, scene by scene, of the movie. And what we think of here is that this person is transmitting their knowledge about the movie to a new set of people who have some ideas about who Sherlock is potentially, and like what car chase scenes are and what murders are, but they've never seen the movie themselves. So the first analysis that you can do is to compare the speaker to the listener and see what kind of coupling there is between them. And when we do this, we have a little bit less power here because there's only one speaker. Yes? I think that's right. I think we definitely did not design it with that in mind, because it was a couple of years later that we even thought to do the second experiment. And some of the regrets we had at that time were that the speakers are not necessarily very engaging storytellers. They're performing a task which is just describing whatever they remember, and it can be a little dull, honestly. And like, if you were going to design a study specifically to do this, I think you would want somebody who is maybe a specialist at storytelling. But in this case, it wasn't, just plain recall. So we have a little less power here, and that's why this map is noisy, probably. You only have one speaker instead of an entire group of speakers, but you do have 18 listeners in this paradigm. And you see these elements of the default network again. One interesting thing about this analysis is you can show that the peak match between the speaker and the listeners is when the listeners are a little delayed from the speaker by a couple of TRs, which makes sense, right? Because the speaker is formulating something in their mind, but then the listener has to actually hear the sentence and imagine it before you can see the best match. And this was done in an earlier paradigm, speaking, listening paradigm, using temporal ISC, so time course match. And then the kind of innovative part of this is that we're using the scene-by-scene pattern match. So we also have scene selectivity for this analysis. You're only seeing voxels in this map if you have the ability to classify individual scenes, right? So that's great. I think the more interesting part of this analysis is the third part of the triangle here. So if you compare the naive listeners to the movie viewing, and this has some similarity to comparing the movie to the speaker, which was the reinstatement analysis. But of course, these people can't be reinstating anything because they haven't seen the original. And in fact, it's not them. They're being compared to a different group of subjects watching the movie. So we think of this as a kind of construction. You're asking, when you're listening to a description of something, how well are you successfully constructing the original experience in mind? And here, we get a map that looks quite a lot like the recollection map, so the default network areas. And what's nice about this is actually there's some selectivity for the person who actually gave you that information. So if you, first of all, if you ask, on the x-axis here is the match between the listeners and the movie, so each person. And then on the y-axis is their comprehension score on a written test that they took after the listening. Right? So the better you match as a listener the movie viewing, the original experience, the better your comprehension. And furthermore, the best match here is going to be to the person that actually did the speaking out of all of the people that watched the movie. And another nice thing about this study is that it's fully replicated with a separate movie within the paper, which is BBC's Merlin, very similar show. And in this one, the best match wasn't the true speaker was the third out of the group. All right. So to take away from here, I would say that the basic idea is that there's a common neural code that can be used as a platform for communicating ideas, and that you can use speech to generate a copy of your experience in other people, which is potentially a mechanism to learn efficiently from the experiences of others. I say efficiently because the movie is like an hour long, and then you listen to it for about 20 minutes, so you save some time. But it's not, it's deeper than that. There are a lot of, I think, there's a lot of value in being able to share somebody else's experience and not have to necessarily go through that entire experience yourself, right? In the case of watching the movie, maybe you wouldn't mind watching the movie, but there are a lot of situations where you benefit from not being there, like a war. You can have somebody tell you about that instead of actually going through the danger and time of experiencing it yourself. And on top of that, when you get information from somebody else, they've already filtered it and transformed it for you. They don't give you an exact copy of their experience. You get from them whatever they got out of the world. So their brain is like a filter that you receive the product of. And this, I think, is a very efficient way to do this. Okay. So a couple of places that this is going that I want to mention. So obviously, I think that understanding this transformation between encoding and recall is really important. And one way, let me just show all these. So one way that we're starting to look into this is by coding the recall in a lot more detail. So, like I said, it's painful that we just average across the entire scene for all of this analysis, and you want to go in and know kind of what's the content of what they described. So, we'll take each sentence or utterance that people make as they're describing the movie and code what kind of content was it. So people do a lot of summarizing, but they also make a lot of precise statements that can really be traced back to individual time points in the movie. People also say things that are just kind of commentary. They're not really summary, they're not really about the events of the movie so much as like their description of what they think the characters are like or feeling. There's kind of different kinds of summaries, and there's also statements that are just false. So it's, I think, important to kind of sift through these and ask for individual sentences that people say. Can we actually observe a difference in the way that the neural signature has changed between the experience and recall? So that will be one way that we go after this. Another question that people often have is, what are the stimulus features that drive these scene-specific neural patterns? A lot of people are interested in this question, other groups. We have just scratched the surface of this by labeling the movie in a lot of detail. What, at every time point in the movie, what location is it, who's there, who's talking, just to try and get a grab bag of features that we can build an encoding model from and try to predict neural patterns. And you can do it pretty well. This is a 50% chance level in posterior medial cortex. We can get to 75% accuracy. But I think a lot of additional work needs to be done on this. And I think people in Hackathon are working with this label set. The data and the labels are all publicly available. Another question that I had was whether the dimensionality of the neural patterns actually relates to the complexity of the movie. So one of the things that we found was if you use SRM on this data, the shared response model, you can adjust the number of dimensions, shared dimensions that you're using for your tests. And we found that our performance was pretty good after about 15 dimensions, and it wasn't getting a lot better. So, of course, there are limitations of the technique itself of fMRI. But a great place to take this would be to ask whether that dimensionality changes over time and whether it's related to the content of the narrative in some way. And lastly, this is a very important question. Why do we segment narrative into events? And I just told you at the beginning that we did it. And we had to do it for this data because in order to match the movie to the recall, they're not temporally locked. So you have to have some way of splitting up the data. But this is a much more interesting question than just a necessity. And Chris Bolisano is going to talk about his very beautiful work on this tomorrow. Okay. So the overall take-home point here is that all of these people are tied together with a neural code. So you have an experience, it generates a neural signature in your brain, that's reactivated when you remember it, and then you're able to transmit that neural signature to another person, even though they never had the original experience. And their brain comes to resemble somebody having the original experience. And this may be a mechanism by which you can learn from the experiences of others. And just remember that every one of these steps is imperfect. And this imperfection is definitely part noise and forgetting. And it's also part optimal transformation and understanding the nature of those transformations at every step, I think, is really okay. Thanks to all of you and to the organizers.
Instead of having the listeners listen to the spoken narrative, read just the transcription of what that is and the similarity?
We haven't done a reading memory study. We have, Uri has some reading studies that compare listening, like auditory listening to reading of the same content. But that's not what you're asking. You're saying instead of being a naive listener, can you be a naive reader?
And
Yeah.
then how much of that dynamics will you recover, and you can, sort of also have that behavioral stuff?
Yeah, I would guess that it's probably very, very similar. If you just had, as long as you had the timestamps for when they were reading a description of each scene in the movie, I think that that kind of information is bimodal. Basically, that's kind of what the speaking and reading, the listening and reading studies show, is that the patterns that you end up with, at least in high-level areas of the brain, are very, very similar between those two modalities. Yeah.
Because I mean, part of the reason that I'm interested is, in a sense, the social aspect is one step removed, right? So you're getting informational transfer without sort of the face-to-faceness of it, and I'm really interested in how persuasiveness differs across different say, information channels.
Yeah, I think that I think it's amodal. I think the content of what you are listening to or reading is going to be the most important thing. So if you have a very flat, poor description, even if it were live, I don't think you would get as good a match to the movie as if you had a really rich and excellent detailed description that was written.
I was wondering about this. So you talk about this transformation from perception to memory. And I'm wondering about sort of like other directions. So if you were to show the listeners who heard the narrative the movie again, how do they watch the movie that's different from a naive movie watcher? Right? Because it's like they just got a bunch of spoilers.
Yeah.
So probably like they have some sort of predictive thing, like they're filling in, pre-existing scheme they got from the speaker.
Mm-hmm.
Have you tried that?
That is ongoing in Aristotle. It is, they call it the spoiler experiment. But yeah, it's a great idea. I think it's a really exciting thing.
So I think one thing that was kind of interesting is, and you mentioned that detective movies in particular are like really archetypal. You've seen one BBC cop drama, and you've seen kind of all of them.
Right.
And so I'm wondering is when you're reading out from PMC, do you think it's like they're imagining the movie, or do you think that it's the semantic content of the movie and they kind of understand what's going on? So it would be something like, do you think you could cross a code from Merlin to Sherlock to Luther or whatever when similar things happen? That might still involve similar imagination. I don't know.
Yeah, I'm not sure that the two things are, like imagining and the semantic content are different. I do think that you could cross-decode to some extent. I mean, if the critical information, as I'm proposing, is this kind of situation-level stuff, like there's a detective there and he's investigating a murder and it's like the morning and he's just come from having coffee and having conflict with his partner. I think that two scenes from different movies that have essentially the same elements like that are going to be more similar because of their shared semantic content than if you're comparing to like a car chase scene, right? But the details of what you're actually seeing matter too. So if you're actually watching that movie scene, like you would still be more similar to somebody else watching the same scene than to somebody watching a similar scene but from a different
I'm just
movie.
wondering also in the compression question, whether there's different kinds of compression you could have. One could be breaking it, when they're compressing in this very similar way, they're breaking it down into, its archetypal features that would
Yeah, I think that's a fair, that is a possible experiment, trying to see whether all of these different presentations of essentially the same situational information actually converge more when you remember them, so they're more similar in memory than they are during perception.
I think there's also an alternative though, where the compression is what would best allow me to re-evoke and be back in the memory again. Like there's a form of episodic compression as well. That could be, how could I describe this in a way that allows me to episodically relive it? That might be different than breaking it down to its individual components.
Yeah. Okay.
So I'm not that familiar with the timescales of that cry, but I'm curious. So you talked a lot about these larger scenes, which are like director's cut scenes. So if you would, for example, that eye tracking, have actually watched while the person was paying attention to Sherlock meeting the corpse and then switched to what's her face, the attack. And then do you feel like you recall that you would have found similar nosimetry, like the nosimetry alignment would have been able to actually go with the
I definitely think so. We coded this at a pretty coarse temporal scale. We have it coded at a much finer temporal scale as well, and that is a low-hanging fruit is to try and see how kind of small can the subscenes go, as long as you can find a match. You know, you have to have enough information in what they said to find the match between the movie and the recall. But I don't see any reason that, as long as you have some way to know that they were remembering that particular moment in the movie, then I think that their reinstatement analysis is valid. Yeah.
Because it's interesting. It seems like that probably would be more out of order, and it might reveal more interesting sort of reconstruction dynamics.
Yeah, I don't have the slides with me, but there are a lot of interesting little things that happen where the director during the movie will give you information out of order, and then you put it together. And when people do the recall, they recall it in the correct chronological order. So there's a lot of solving like that people do kind of without even thinking about it. Yeah.
I'm sorry if you mentioned this during this talk, but do you have analysis where you look at when people are talking, what part of the brain do they use to maximize the correlation between watching and then the listener's brain? Does that make sense? So like, you could say someone is a very good storyteller, and then their story will make the listener sync up with the brain that the storyteller is watching, right? But I'm wondering if there's a part of the brain that's making the person the storyteller.
I don't think I am understanding.
It's like a mediation analysis, whether there's a part of the brain that mediates the extent to which they might be giving highest bits of information that matches the movie to telling the story.
Yeah, no, it's an interesting idea. We've never done a mediation analysis like that.
I was thinking more about simply correlation between the brain when the person is telling the story and the similarity between the brain that the person is watching the movie and the person who is listening to the story.
I think maybe one way to answer that is, so I showed you the pairwise correlations of the different groups, right? But one of the, yeah, so you can also do a three-way similarity analysis because it definitely could have been the case that the similarity between movie and speaking is like a different pattern than what's similar between movie and listening, right? Or like each of these three could have been different. So in this analysis, we look explicitly at whether the patterns are the same, whether you can do the classification in three directions. So it's actually the same pattern of activity that's shared between movie and speaking, that's also shared between movie and listening and between speaking and
There's
listening.
also a silver paper too. The speaker communicator storytelling one, where you scan, or it wasn't you, but there is one. Is that the
Isn't, so just to follow up on that, is the idea that you have like, so maybe speakers who get better responses from listeners are doing extra theory of mind work, and so yeah, right. So like, could you see that?
I guess so. Then you would be doing like a univariate analysis at the on the speakers.
Yeah.
Well, we didn't, but I think I understand. Yeah, that's a good idea. So you're looking for regions that it's not necessarily a pattern match between the speakers and the listeners or the other groups, but it's some kind of like extra work that's being done by a region that makes them more appealing or more successful communicators. I don't have that analysis.
I'm not a good storyteller.
But you have humor. I like that guy in that video for
So maybe we'll take a 5-minute break and get started with items after that. So let's thank Janice one more time.